Hi, I'm Ethan.
I'm Brett.
I'm on.
And here today we're going to talk to you about recovery, re-crystallisation and grain growth. The learning outcomes are, by the end of this presentation, you should be able to understand the following.
Identify the three strategies of strengthening a material, the difference between a single and polycrystal structure, understand why a smaller grain size is stronger than a larger grain size.
And you should be able to tell the differences between substitutional and interstitial solid solutions, and also describe the differences between larger and smaller impurities in lattices of metals.
You should also understand the many different processes of cold works.
The three strategies for strengthening. The first of which is to reduce the grain size. And what needs to be understood first is what a slip plane is. So a slip plane is the location within a structure which allows dislocations to travel from where they are formed. The grain boundaries are another thing that needs to be known, which is the regions between slip planes which work as a barrier to stop slip. They act as an obstacle to dislocation motion. So what we have here, we have the dislocation symbol here. So you can see that the slip planes, which are these lines along here, in a single crystal are all orientated in the same direction. So if a dislocation occurs, it's able to slip all the way along the slip plane to reach the edge of the crystal, which is when we have a potential fracture of the structure. If we move on to the polycrystal structure, however, you can see that there's all different sections. So all these different sections are orientated in different directions as opposed to the long lines of the single crystal. So this means that if a slip occurs inside of one of the polycrystal structures, it can only go up until the grain boundary, this being the grain boundary, because the grain boundaries are a barrier to slip, so they stop it before it goes further. So it essentially just means that the amount that the structure slips is determined by how far the dislocation can travel along a slip plane. So the smaller the grain size, the smaller the size of the slip plane, the more grain boundaries in between, and the less effect caused by a dislocation within the structure. So here we have a piece of metal that has been quenched. So quenching is one of the main ways to reduce the grain size of a structure. So here you can see after one quench, the grain size is very thick, and then from the first quench, second quench, third and fourth, you can see the grain size of the metal getting smaller and smaller to the point where you can't really tell the difference between the third and fourth quenches. And then moving on, we have just an example of the difference between coarse grains and fine grains. So you can see that with bigger grain size, there are less grain boundaries compared to fine grain size. So there's more barriers to stop slip with fine grains compared to coarse grains. So here we have the Hall-Petch equation, which shows that the strength of a metal, the yield strength, is proportional to the diameter of the grains in the sample. So essentially it just means that the smaller the grains, the stronger the yield strength. So we have a K value within this equation, which is different dependent on which material is being used. So we've got a table here of all the different values. So then moving on to an example question, we've got one here which is just that the yield strength of a sample of low carbon steel, so from the previous page we'll be able to grab our K value. The yield strength is 20 megapascals, so the diameter of the grain is 3.8 nanometers, and we need to find the starting stress for the dislocation movement, which is sigma O here. From the table on the previous page, the K value of a low carbon steel is 3.07. Given the values, one must put the values into the Hall-Petch equation from here, and it's just simple substitution here, resulting in our answer of negative 4,960 pascals.
The second process for strengthening materials is forming solid solutions. By forming a solid solution, we're putting atoms within a lattice, either substitutionally or interstitially. Substitutional solid solutions are when impurity atoms substitute another atom within the lattice. As we can see here, we have a majority of silver atoms within a lattice and substituting copper atoms in place of those silver atoms. This causes lattice strains that are present when the impurity atoms are found, and they distort the lattice to cause strains on the system. Interstitial solid solutions, however, are when there are impurity atoms that are dispersed between the lattice. So here we can see that the solvent metal atom and then the solute element atom are dispersed interstitially between that lattice. With smaller impurities, the substitutional atoms have a tendency to focus on dislocation causing compressive strain. So as we can see here, reducing the mobility of these dislocations increases the strength, as there is a more compressive strain on the surrounding atoms. This impurity is located adjacent to the dislocation line and above the slip plane. With larger impurities, substitutional atoms that are larger focus on areas of dislocation and they cause tensile strain, as we can see here. The solute atoms diffuse to locations and wrap themselves around them, reducing the overall strain energy. This impurity is situated below the slip plane.
So, cold work. The definition of cold working is the deformation in an alloy, which is followed by work hardening, which increases the strength of the material. Cold working is ideally used as a final step for a material when it needs tight dimensional tolerance and manipulation of the alloy. Adjusting the amount of deformation and the rate of deformation allows for the control of both the strength and the ductility of the alloy. And in summary, cold working is a method that is mainly done at room temperature or elevated temperatures, which increase the ductility of the material. So some processes of cold working are cold rolling, which accounts for the greatest tonnage of cold working, and this method is mainly used for sheets, strips, or bars and rods of metal, which are created through this process. Another method of cold work is cold forging, which large quantities of product are squeezed through a die cavity that is in a desired shape. So in this example, the die cavity is in a cylindrical shape. So when the metal is being squeezed through, it fills up the die and comes out in the desired shape, as you can see here. So sizing is another process of cold working where it's similar to cold forging, and it is squeezed through a die where it becomes the desired thickness that we require. So another method of cold working is extrusion, where where the metal is usually in a cylindrical shape and it is forced into the billet, as you can see here, and it goes through a die which is in the desired shape that we require the material to come out as, and it is then forced through and it becomes the desired shape that we require. So the impact of cold working is that the deformation and the defects are permanent on the metal, which results in the crystalline makeup to change. Those defects that cause the crystalline structure to change results in the crystals to move within the metal structures, which results in resistance to further deformation by other sources. So in this example question here, we have two unformed cylindrical specimens where an unspecified alloy is where we are reducing the cross-section areas. We are given the two radiuses for the initial specimen, and we are also given the initial radius of the second specimen. We then have to find what the deformation of radius would be on the second specimen. Now, to go about this, first of all, we would have to work out the percentage of the cold work on the materials. Where first we'll find the initial area here and the area of deformation divided by the initial area, and we times it by 100 to give it to us in a percentage value. So the area of a cylindrical shape is pi r squared, and we just simply insert this and then insert the units we're given in. And changing the units to meters or millimeters does not matter because we are finding a percentage value rather than an SI unit. And then after this, using this percentage value, we then input, we then use this formula here where we are finding the radius of deformation here. What we do here is then rearrange our values so we only have the radius deformation on one side and the rest of the values on the other side. Then we just simply input the values in, and then as you can see here, we calculated 6.47 millimeters as the value, and that's how you do it. And here are our sources that we have used for this presentation. Thank you very much for listening to this presentation.